Today's lecture is on X-ray projection imaging. Let's look at the objectives for today. At the end of this lecture, students should understand how geometry-related issues like magnification and inverse square law affect image appearance in projection imaging. Students will learn about image quality-related issues like contrast from both the subject and image detector points of view. Students will learn about ways to improve contrast using grids for scatter reduction and also learn about image degradation and a few of its causes. Students will also learn about image receptors like screen film systems, computed radiography systems based on photostimulable storage phosphors, digital radiography systems based on cesium iodide and amorphous selenium. We shall also touch on charge-coupled devices and complementary metal-oxide semiconductor imaging systems, and then finally classify image receptors as direct and indirect detection systems. Here are a few pictures of projection X-ray systems. On a broad scale, we shall be looking at three parts of a projection system: the X-ray beam as it exits the collimator, the patient, and then we have the image receptor or detector. In X-ray imaging, we are imaging a 3D object and displaying it in 2D. The appearance of the 2D image depends on various factors related to geometry and exposure at the image receptor. Geometry-related issues arise because we use a point source of radiation that spreads out as it reaches the image receptor, and also because the object is between the source and image receptor. Exposure at the image receptor is determined by the tissue thickness in the path of the beam. Thicker tissues mean more attenuation of the X-ray beam. Also, different densities and atomic numbers of tissue in the path of the beam affect the image appearance. The type of image receptor used as well as the presence of a grid will also affect image appearance. This figure shows the beam, the patient, and the grid, and also the detector arrangement. Let's look first at geometry issues. Because the object is between the point source and the image receptor, geometric effects become important. First, there is the issue of magnification. The image of an object is magnified when the object is at some distance from both the signal source and the image receptor. Second, when using a point source for imaging an object, the beam spreads out, leading to reduced intensity at the image receptor. We can look at each of these problems in detail next. The effect of magnification is demonstrated on this page. We can see that by moving the object location relative to the point source and image receptor, different levels of magnification can be achieved. When SOD is equal to SID, the magnification is 1, so image represents true size of the object. I have an example for you showing the magnification for the SID and SOD numbers. Magnification can be increased by moving the object close to the source, but because an image receptor has a limited field of view, moving the object too close to the source will lead to the image being outside of the field of view. Moving the patient too close to the source will also result in an increased patient exposure. Another problem connected to the point source is the blurring of the edges of the image. The image of the edge of a sharp object is blurred depending on the object position from the image receptor. This is because of the spatial extent of the so-called point source. So on these figures, you can see the effect clearly when the edge of the object in figure A is more spread out compared to the edge in figure B. By getting the object close to the image receptor as in figure B, the blur is reduced. Another consequence of imaging with a point source is that as the distance from the point source increases, the number of photons decreases due to the inverse square law. This geometric effect arises because as the distance increases, the X-ray beam spreads out and the area of the region the X-rays pass through increases in a squared fashion for each unit change in dimension. This is shown in the top figure. Knowing how to account for the inverse square law is an important skill to have. Let's look at an example. Suppose you have an exposure of 100 milliröntgens at a distance of say 2 meters from a point source. What is the new exposure at 4 meters from the source? We can use the formula for inverse square law shown on the bottom image. From this calculation, you can have an answer of 25 mR. So you see that the exposure is decreased by a factor of 4 when the distance is doubled from 2 to 4 meters. Inverse square law problems can be simple if you recognize that if distance is doubled, the exposure is cut in 4, and if distance is tripled, the exposure is cut by 9, and so on. You can also go the other way with this exercise. If distance is cut in half, exposure should increase by a factor of 4, and if distance is cut by a third, exposure should increase by a factor of 9, and so on. Once an image is acquired and displayed, we often refer to the quality of the image. Image quality is a subjective term that applies to how clearly the image displays information about the anatomy, physiology, and functional capacity of the patient. A more useful term is image clarity. Image clarity is a measure of how well information of interest is displayed in an image. Clarity is influenced by four fundamental characteristics of the image. These are contrast, noise, and sharpness, distortion. We shall start with contrast next. There are two types of radiographic contrast: subject contrast and detector contrast. Let's look at how subject contrast affects radiographic contrast. Factors affecting subject contrast can be classified as intrinsic and extrinsic. Intrinsic component of subject contrast relates to the actual anatomical or functional changes in the patient's tissues, which gives rise to contrast. That is, the patient arrives at an imaging center with intrinsic physical or physiological properties that give rise to radiographic contrast. An example will be ribs in contrast to lung tissue. This figure shows two objects A and B in a simulated patient. Because of the different attenuations of the two objects, the number of X-rays reaching the image receptor behind each object is different, leading to different contrast levels. Extrinsic factors relate to how the image acquisition protocol can be optimized to enhance radiographic contrast. Possible protocol enhancements include changing the X-ray energy or injecting an iodine contrast as in CT or gadolinium contrast as in MR. Intrinsic subject contrast depends on the types of tissues in the patient. On this slide, we have some tissues and their effective atomic numbers and densities. Remember that contrast is due to the relative contributions of the photoelectric effect and the Compton effect. At lower diagnostic energies, the photoelectric effect dominates over Compton effect, leading to more contrast when different atomic numbers are present, and this is what we see in mammography. At higher energies, the Compton effect dominates over photoelectric effect, so that while the effect of different atomic numbers continues to play a role, the contribution of different tissue densities is also enhanced. The next type of radiographic contrast is due to the detector. When a patient is imaged with X-rays and the X-rays strike a detector, the type of detector is important in determining how the image will look. Different detectors have different contrast responses. On this figure, we have two types of detectors as shown by their relative response to an X-ray signal. One detector shows a sigmoid curve, meaning it amplifies the signals in the steep areas of the curve and gives a linear response in that area. The other detector shows a linear response across the entire X-ray signal range. A sigmoid curve is characteristic of a screen film type detector, while a straight line response is characteristic of a digital detector. Detector contrast has a modulating effect on radiographic contrast and affects how the displayed image will look. An important factor that affects radiographic contrast is scatter radiation. On the next few slides, we shall look at how scatter is controlled and reduced. Before we get into that, we can first look at why scatter is important. Radiographic contrast is affected by scattered photons reaching the image detector. Scattered photons contribute to increased noise in the image. Noise is characterized by the standard deviation of the pixel signal. Contrast is calculated as the difference between a background ROI and an object ROI divided by the background ROI. This slide shows two contrast formulations, one with scatter and one without. The ratio of scattered photons and primary photons is called the scatter to primary ratio SPR. The bottom graph shows how the radiographic contrast is degraded by increasing scatter to primary ratio. Let's take a closer look at scatter to primary ratio. Scatter to primary ratio depends on the field of view used for imaging. Selecting a large field of view means more scatter radiation. Using the smallest field of view necessary for anatomic coverage reduces scatter and improves image quality. It also reduces occupational exposure. For a given field of view, larger patients produce higher scatter to primary ratios than smaller patients. The figures on this slide show how scatter to primary ratio changes at different field diameters or fields of view for different patient thicknesses. It is clear that the largest field sizes produce the largest scatter to primary ratios for different patient thicknesses. Scatter in an image is usually controlled by anti-scatter grids. There are several types of grids: Three types are shown here: linear parallel, linear focused, and crossed grids. Focused grids are designed to be used at a particular source to image distance SID or focus to grid distance as shown on the bottom figure. Parallel grids can be used when the SID is far enough that the beam appears to be parallel when it reaches the image receptor. Cross grids may be parallel or focused and allow for more effective removal of scatter because of the presence of the extra grid lines. Grids are made of high atomic number materials like lead. The purpose of the grid is to block scatter radiation from penetrating the septa or grid wall and contributing to noise in the image. Grids could be stationary or moving. Moving grids are called Bucky grids. Grid frequencies are typically about 60 lines per centimeter. Some higher frequency grids are also available. When moving grids are used, they move with the Bucky so that the grid lines do not appear in the image. Some high frequency grids are stationary because the grid septa is small enough that the grid does not appear in images even when stationary. Having a grid between the patient and image receptor means that while the grid stops scattered photons from interfering with the image, it also stops primary photons from getting through to the image receptor, reducing the signal on the receptor. The exposure must be increased to account for the loss of signal at the image receptor when a grid is present. This leads to increased patient dose. So using a grid means more exposure is needed for the image receptor to reach the correct optical density in the case of screen film systems. The Bucky factor is a way to quantify the contribution of the grid to patient dose. Bucky factor is defined as the exposure with grid divided by exposure without grid. The table shows the Bucky factor as an increase in exposure. Bucky factors range from 3.5 to 5 depending on the KV and grid ratio. Grid ratio is the grid height H divided by grid spacing W. The figure shows the measurement locations for grid height and width. Grid ratios are typically 8 to 1 or 12 to 1. The effect of grid on radiographic images can be measured by various means. Contrast improvement ratio and contrast degradation factor are two ways of measuring this effect. Contrast improvement ratio is the ratio of contrast with a grid present to contrast without a grid. It is shown as the improvement in contrast in the top table. So the contrast improvement for a 12 to 1 grid ratio at 120 kV is 3. At 70 kV, the improvement is even better at 5.25. The bottom right figure shows the scatter transmission for different grid ratios. The contrast degradation factor refers to the reduction in contrast due to scattered radiation. Contrast degradation factor is of less importance in digital radiography because digital images can be adjusted to enhance contrast. Based on what we have learned so far about grids, we can conclude the following. First, all grids improve contrast significantly. Second, the effectiveness of a grid increases with grid ratio. And third, patient exposure increases with grid ratio. There are other methods of reducing scatter in an image. By moving the patient away from the image receptor, an air gap is created that reduces scattered radiation to the image receptor. Increasing the air gap distance also has the undesirable effect of increasing the magnification of the patient's anatomy. These figures show the effect of increasing patient distance from the image receptor. Other disadvantages are reduced coverage on the image receptor and loss of spatial resolution due to increased focal spot blurring. There is also increased patient dose as the patient is moved closer to the X-ray source. Another method that can reduce scatter radiation is to use slot scan radiography. Slot scan radiography can be regarded as a gold standard in scatter reduction methods. This method works very well because a very small field is being imaged at any point in time as the figure shows. Most scatter is prevented from reaching the image receptor and the image is produced by scanning the small slot across the entire field of view. In addition to excellent scatter reduction, slot scan radiography also does not require a grid and therefore has the potential to be more dose efficient. Disadvantages to this method includes longer acquisition times, increasing the chance for patient motion. Also, because higher tube currents are needed when using a narrow scanning aperture, there is more tube heat loading. Let's now look at image degradation and some of its causes. We shall first look at image degradation due to distortion. Distortion is present to some degree in every diagnostic image. Image distortion is caused by unequal magnification of various structures in the image. In radiography, for example, structures near the intensifying screens are magnified less than those farthest away, as shown in this figure. You can use these magnification differences to gain a perspective of depth among different structures in an image. The same formula for magnification applies in each case. Image degradation can also be due to the geometry of image formation. If the X-ray source was a true point source, there will be little blurring of the image. But because the X-ray source is not truly a point, every image introduces an element of fuzziness or blurring to well-defined or sharp boundaries in the patient. This blurring is described as unsharpness and is depicted in the figure. Unsharpness or blur is a measurable characteristic of images. It is worse when the object is closer to the source than when the object is closer to the image receptor as shown in the bottom figures. Image degradation also occurs because of motion. Motion occurs because of involuntary physiologic processes or voluntary actions of the patient. Voluntary motion can be controlled by asking the patient to stay still. Involuntary motion, especially motion of fast-moving structures, is more difficult to control. One way to freeze motion is to use short exam times. In general, short exam times are desired to reduce both voluntary and involuntary motion if the tube current allows it. The table shows some anatomic structures and their speeds. Grades are another cause of image degradation. The term grade cutoff is used to describe the loss of primary radiation caused by improper alignment of a radiographic grid. There are three possible grade cutoff errors. The first is parallel grade cutoff, where a parallel grid is used instead of a focused grid, or when a parallel grid is used at too close a distance. The second is off-distance cutoff. This occurs when a focused grid is used at a wrong distance. The margin of error for target grade distance is narrow for grids with a high grade ratio and wider for grids with a smaller ratio. The effects of off-distance cutoff are more severe when the target grade distance is shorter than that recommended, and less severe when the target grade distance is greater. Off-center cutoff or lateral decentering happens when a focus grade is used at the wrong lateral position. These figures illustrate each of these scenarios. In radiography, receptor and sharpness can cause poor image clarity. Receptor and sharpness is determined principally by the thickness and composition of the light-sensitive emulsion of the intensifying screens. This is true for screen film radiography. These characteristics influence not only receptor and sharpness but also the sensitivity of the screens to X-rays. With increasing thickness, for example, the sensitivity improves but unsharpness also increases. So there is a trade-off between sharpness and sensitivity of film emulsion due to thickness of the emulsion. This figure shows an image acquired on three different image receptors. The final image receptor shows a reduced unsharpness compared to the image receptor with larger pixels. The type of image receptor used for acquiring an image also plays a role in the image appearance. Let's look at the types of image receptors used in imaging. Several types of receptors are used in projection radiography. Traditionally, screen film systems were used for X-ray imaging. Then, computed radiography or CR systems were introduced. Currently, most radiology departments use a form of direct digital radiography imaging system. Let's look at each of these in more detail. Although screen film systems are less common these days, for historical perspective and context we shall learn about them. Screen film systems consist of a light-sensitive emulsion sandwiched between two intensifying screens. Screens were historically made from calcium tungstate, but it's more common now to have rare earth screens made of gadolinium or lanthanum. The light-sensitive film is made of a base of cellulose and an emulsion of silver halides. This figure shows a diagram of a cross-section of a screen film system as well as micrographs on an emulsion layer showing some silver halide grains. Screen film systems were slowly replaced by computed radiography or CR detectors. CR was introduced in the late 1970s and saw increased use in the late 1980s. CR systems are photostimulable storage phosphors that store energy for later release. Storage phosphors are made of a compound of alkali fluorohalides doped with a rare earth element like europium. The phosphor is exposed to X-rays and stores the X-ray energy in a luminescent center in the crystal structure. The exposed CR plate is placed in a laser reader where the image on the plate is read out. A computed radiography or CR readout mechanism is shown on this slide. This mechanism allows the exposed CR plate to be translated through rollers both vertically and horizontally. A red laser light stimulates the luminescent centers to release blue-green light. This light is collected by fiber optic light guides and sent to a photomultiplier tube. The photomultiplier tube produces an electronic signal that is digitized and stored as a pixel value. For every spatial location on the imaging plate, a corresponding grayscale value is determined that is proportional to the locally absorbed X-ray energy. The plate is erased by a bright white light and can be reused. To put things in perspective, screen film systems are typically 400 speed systems, while CR systems are usually 200 speed systems. The screen films and CR systems we have been learning about are analog imaging systems. Let's now learn about digital imaging systems. Charged coupled devices or CCD detectors form images from visible light. A CCD chip has an array of discrete detectors and electronics etched into a crystalline silicon surface. CCD arrays have a matrix of 1024 or 2048 detector elements on a 6.25 cm squared surface area. Larger chips and larger matrices of 36 squared centimeters are available but are more expensive. Higher quality CCD radiographic systems typically make use of cesium iodide input screens with improved X-ray detection efficiency and light capture efficiency. Less costly systems use gadolinium oxide screens. The bottom right figure shows an illustration of a CCD system. The readout is shown in the top figure. Readout is done line by line. The bottom left figure shows a comparison between a CCD graph and a characteristic HD curve of a 400 speed screen film system. The CCD system is more sensitive to radiation and has a wider dynamic range than screen films. An alternative detection system to CCDs is the complementary metal-oxide semiconductor or CMOS light-sensitive array. These are based on a crystalline silicon matrix and are like random access memory chips. They include built-in photosensitive detectors, storage capacitors, and active readout electronics. Their similarity to a RAM allows for random access to any detector element on the chip in a read-only or read and erase mode. This feature enables CMOS systems to potentially perform automatic exposure control, a capability that is not easily performed with a CCD photodetector. CMOS detectors have more electronic noise than CCDs and a smaller field of view due to construction challenges. Current applications are in the area of imaging specimen tissue samples from surgery. Current digital radiographic image receptor systems are built around a thin-film transistor or TFT active matrix array. There are two types, one that uses a cesium iodide scintillator to produce light from X-rays, and the other uses amorphous selenium to directly detect X-rays. When a cesium iodide scintillator is used to produce light from X-rays, the light collection element is an amorphous silicon-based TFT photodiode. Large area TFT arrays are divided into individual detector elements called dexels. The percentage of the dexel phase that is sensitive to light from the cesium iodide scintillator is called the fill factor. Fill factor is approximately 80% for dexels of 200 micron size. Spatial resolution in DR is dexel size limited. As dexel size is reduced, spatial resolution improves but at the expense of patient dose. With smaller dexels, the fill factor is reduced and X-ray intensity must be increased to maintain adequate signal strength. In the second type of DR system, the X-ray collection material is amorphous selenium. With the use of amorphous selenium, X-rays are converted directly to charge and transferred to the TFT and storage capacitor. There is no need for an X-ray scintillator. These two systems, based on the use of cesium iodide and amorphous selenium, sets the background we need to classify image receptors. We shall do that next. DR systems may be classified as either indirect or direct detection systems. An example of a direct system is one that uses amorphous selenium and a thin film transistor for readout of charges. An example of an indirect system uses cesium iodide with amorphous silicon-based TFT photodiodes to read out the signal. Other examples of indirect digital systems are CCDs and CMOS-based digital detectors. Direct digital systems containing amorphous selenium are commonly found in mammography image receptors. Better spatial resolution is achieved for direct detection than for indirect detection due to the light spread in an indirect system. This figure shows the spread of signal light from the two systems. Let's finish up with a few questions. First question. When imaging a patient in mammography, the best spatial resolution can be achieved by using which of these? Your choices are: first choice, a detector based on cesium iodide; second choice, a detector based on amorphous selenium; third choice, a PSP-based computed radiography detector. The correct choice is a detector based on amorphous selenium. Second question. Which of these is not a method that can reduce motion and sharpness? Your choices are: first choice, higher KVs and lower tube currents; second choice, using shorter imaging times and higher tube currents; third choice, using patient restraints. The correct answer is higher KVs and lower tube currents. Next question. Which of these is not true about grids? Your choices are: first choice, all grids improve contrast significantly; second choice, the effectiveness of a grid increases with grid ratio; third choice, grids improve spatial resolution; fourth choice, exposure of the patient increases with grid ratio. The correct choice, which is not true about grids, is that grids improve spatial resolution. This is the last slide. Thank you for watching this presentation.